So in this video we're going to look at our second core practical around rate of reaction. Now this video involves a reaction between hydrochloric acid and sodium thiosulfate. Hydrochloric acid has the formula HCl and sodium thiosulfate is this formula here, Na2S2O3. Now when these two substances react together they make the four products, sodium chloride, sulfur dioxide, sulfur and water. Now you might be thinking to yourself, after the last rate of reaction core practical where we collected the volume of the gas given off, we could use the volume of sulfur dioxide gas produced, and I suppose we could do that. The reality is this produces very, very small amounts of products. We're doing this with very dilute reagents. So we're not going to see really a bubble, although you might expect it to. The way we're going to monitor the rate of this reaction is by looking at how quickly this sulfur solid is produced. A solid produced in a reaction is a precipitate. So what is a precipitate? A solid produced in the reaction. Now that will make the solutions go murky, go cloudy. Sodium thiosulfate, as you'll see in a moment, is a colourless liquid when it's aqueous and when it's dissolved in water, and hydrochloric acid when it's dissolved in water is a colourless liquid. So two colourless liquids are on the left, but they produce this sulphur which is going to make the solution go cloudy. So what we're going to do is we're going to put the reagents on a conical in a conical flask, one of these, and we're going to put that on top of an X like that, and we're going to look down. Through the flask, and when that X disappears, that X will disappear because of the sulfur solid produced. Quickly, a hypothesis, because we're changing the concentration of the thiosulfate. The higher the concentration of sodium thiosulfate, the quicker the cross will disappear, because the quicker the sulfur will be produced, because the quicker the reaction will go, and that's obviously because of particle theory. We'll possibly talk more about that later. So on the next page here we've got our method, a detailed method, and a results table. So first off, put 10 centimetre cubed of sodium thiosulfate in a conical flask and add 40 centimetre cubed of water. So this is our experiment one. Now in each experiment it's important to say that the total volume of sodium thiosulfate is 50 centimetre cubed. So we've got 10 and 40 equals 50. So in each occasion, 20 and 30 equals 50. In each occasion we are reacting 50 centimetre cubed of sodium thiosulfate solution, the only difference being the concentration changes. Okay, we're reacting 50 centimetre cubed of sodium thiosulfate solution with step 2, measure 5 centimetre cubed of dilute hydrochloric acid. So we are using 50 centimetre cubed of sodium thiosulfate, 5 centimetre cubed of acid, and the thing we are changing is the concentration of the thiosulfate. So by changing the volume of thiosulfate and water, we are changing the concentration, and that's really important. Okay. So let's do experiment 5, this last one here. Okay, so we're going to measure out, instead of measuring out 10 centimetre cubed, we're measuring out 50 centimetre cubed of sodium thiosulfate. And I've already done that, and that's in this measuring cylinder here. We use measuring cylinders to measure out. And I've got my 5 centimetre cubed of acid in a smaller measuring cylinder there. So let's just move the method out of the way, and let's bring our conical flask. Got our conical flask here, and we're going to put it on an X there, and let's put them in. So first off, I'm going to put my 50 centimetre cubed of sodium thiosulfate solution in. That's neat, so I haven't diluted it any further. Okay, and we're going to need a stopwatch to start that, so we can time it. Let's try and get that in focus. That's as good as I can get the focus, so we're ready to go. I've got my 50 centimetre cubed of sodium thiosulfate in there. I'm going to start the watch, and I'm going to tip in the acid and give it a swirl, and we'll try and keep it in focus. Now, the important thing is, now I've given that initial shake, I'm not going to shake it again, because obviously the more I shake it, the more collisions I make. And that wouldn't be a fair test. I'm going to shake them all the same. Every reaction is going to be shaken in the same way. So you see it's starting to cloud off a little bit now, and I'm going to stop that as soon as I can't see that X anymore. Okay, so it's getting cloudier and cloudier and cloudier. So as soon as I can't see that X, I stop the watch. I'm getting close to it now, aren't we? Okay, can I see it? Still just about see it. Can't see it anymore, let's stop that. Okay, so I've now stopped that on 36.72 seconds, or we'll say 37 seconds. I think that's more than accurate enough. So let's record those results. That was 37 seconds. Now if I'm going to do this experiment accurately, then it will be entirely reasonable to repeat that experiment a couple of times and then average the results. Because there is obviously a margin of error, deciding when the cross can be seen or can't be seen, and when you start the watch, maybe how much you shake it and whatever else. Anyway, now rather than video the other 4 experiments, I've done those already. Okay, so the first experiment took 4 minutes and 29 seconds. Now we've got to be careful as we record this. We're going to record in seconds, so 4 minutes is 240 seconds. So 4 minutes and 29 seconds is going to be 269 seconds. The second experiment was 1 minute 47, so that's going to be 107 seconds. Then that was 66 seconds, and that's 46 seconds. So the next thing we have to do is plot a graph of the volume of sodium thiosulfate, and that's going to go on the horizontal axis. Your book says horizontal. Against the time taken for the cross to disappear, and that's going to be on the vertical axis. Your book is that way around. Okay, so the next page is some graph paper, so we can get started. Now I've already labelled up some axes for you. I've got the thiosulfate and the water down here. I've got the time up on that axis there. Now it's important we plot our graphs with pencil, and we take our time and we find out exactly where these crosses go. Okay, so the first one was 269 seconds for the 10, so there's our 10 there, and here's our 250. Now there's 10 little squares between 250 and 300, so 50 increments if you like, so each little square is going to be 5, and we need to go to 269, so each one's going to be 5, so it's going to be 255, 260, 265, 270. It's going to be just there, just a tiny bit under the 270 line, but an X will do it absolutely fine. So looking at that, it looks like although I spent so long getting the 269 in the right place, I've actually strayed off my 10 axis, haven't I? And this is one of the reasons, it's so easy to do this from plotting graphs. One of the reasons we always plot in pencil. So we can rub it out without having to re-scratch the graph. So let's move that over just one, and let's get a rubber and give that a good rub out there. Okay, so easily done. I've got quite an old rubber here. It's not rubbing particularly well, never mind. But we'll give that as rub out as best we can. Okay, let's carry on with our plotting now. 107 seconds was the next one. So let's find 100. There's 100, and each little square is 5. Okay, so it's going to be just roughly halfway between the 105 and the 110. There we go. Next one, 30 and 20 was 66. So 50, 55, 60, 65, tiny bit above the 65 line, but pretty much bang on it. And the next one, 46 seconds was the next one, so that's going to be just a tiny bit under. There we go, that's bang on 46. And 37 for our last, so 25, 30, 35, 37. And there are our points plotted. Now we've plotted that, we need to do our line of best fit. Now lines of best fit are either dead straight lines or really smooth curves, So this is going to be a curve, isn't it? It's going to come down a bit like this. So, beautifully smooth curves. Remember, it doesn't have to go through every point, but looking at this one, I'm just going to move this around a little because it's going to be easier for me to plot it rather than bending my arm too much. And it's okay to move the paper quite a bit, like so. But that data looks reasonably accurate, so we've got a nice smooth curve going through that data. Okay, so we've got some questions to finish off underneath, but I think most of them are probably fairly obvious. Which mixture of thiosulfate and water was the most concentrated? The most concentrated was the 50 of thiosulfate, Na2S2O3, and 0 H2O. And the least concentrated was the 10 of thiosulfate, sodium thiosulfate and the 40 of water. And they both add up to 50, so exactly the same volume of both solutions of thiosulfate, but with different concentrations. How does the speed of reaction vary with concentration of reactants? Well, high concentration equals fast reaction. Do you think the rate also depends on the concentration of the acid? The answer is yes, absolutely it will. How do we change the experiment to do that? Well, we'd always use use 50 of sodium thiosulfate and 0 water, but then use maybe 5 HCl, 5 hydrochloric acid and 0 water, and 4 HCl and 1 water, maybe then 3 HCl and 2 water. So we're doing exactly the same. We're just changing the volume of hydrochloric acid and water. Always adds up to 5 again. Okay, and then we can do the fifth one with a 1 HCl. 1 HCl and 4 water. 5 experiments, just changing the acid that time. Okay, and our last question, last 2 questions. Why do you think changing the concentration of thiosulfate and acid will change the rate of reaction? Well, high concentration, it's all about particle theory. High concentration equals lots of particles. If there's lots of particles, there's lots of collisions. If there's lots of collisions, that equals fast reaction. What other factors will alter the rate of this reaction? Well, temperature. That's the main one. And there is our second core practical about rate.